Okay, so square matrices. So we'll define what a square matrix is. We'll talk about multiplication of square matrices and then inverses. Non-square matrices can't have inverse. So a square matrix is a matrix that's got the same number of rows and columns. The identity matrix of size n is an n by n matrix with ones down the main diagonal and zeros elsewhere. So I2 is a 2 by 2 matrix that looks like this. I3 is a 3 by 3 matrix that looks like that, etc. So every square matrix has what's called its main diagonal, which is just like that or like that. So one's down the main diagonal, zeros elsewhere, that gives you an identity matrix. Multiplication, if you have square matrices of the same size, you can multiply them by each other, and some of the usual rules for arithmetic hold, right? So if you multiply a matrix by a identity matrix, you get the matrix back. You can distribute matrix multiplication, and you can do associativity, right? So it doesn't matter what order you where you put the parentheses here. If you multiply m1 times m2 and then times m3, or m2 times m3 and then m1. Commutativity does not hold, right? So, oops. Right, this matrix times that matrix is not equal to the matrices multiplied in the other direction. So you have to be careful about that. And not all matrices, square matrices, have a multiplicative inverse, right? And multiplicative inverses, this allows us to do division. So you're used to, say, if 7x equals 5, how do you find the solution? Technically, what you do is you multiply both sides by 1/7, which is the multiplicative inverse of 7. And then you can say, well, x is equal to 5/7. So division is multiplication by the multiplicative inverse. So not all matrices have inverses, though, although some do. So an inverse for a square matrix, and you have to be a square matrix to have an inverse. You have another square matrix of the same size, so that when you multiply them together, you get 1, right? Again, like 1/7. Oops, what's going on there? 1/7 times 7 equals 1. Right? A multiplicative inverse means when you multiply it together, you get the identity. So these two are inverses. How do we show that they're inverses? Well, two matrices are inverses means that when you multiply them together, you get identity matrix. So 1 times -2 plus 2 times 3/2, which gives me 3. 1 times and then we multiply first row times second column. So 1 times 1 is 1, plus 2 times -1/2, which is -1. 3 times -2 is -6. 4 times 3/2 is 6. 3 times 1 is 3. 4 times -1/2 is -2. And what do we get? We get the identity matrix. So these two things are inverses, because when you multiply them together, you get the identity matrix. Now the question is, if you've got a square matrix, how do you find the inverse? So the idea is that we want to do this multiplication. Well, what that means is there's sort of two different things here. One is that m times the vector AC should be equal to 1, 0, and m times the vector BD should be equal to 0, 1. Right? Because m times AC, you take the first row of this times that gives you this number. And then you can take the second row of m times this vector, and that gives you this vector. M times BD, so m times the second column means take the first column of m, multiply it by BD, and that should give you this number. Take the second column, second row of m, multiply it by this, and that should give you 1. So, and we saw how to do this, right? We're looking for unknowns that are equal to these things. So what we want to do is set up that augmented matrix, because we have the same matrix here. We want to solve what numbers give me this matrix times a vector gives me this vector, what vector times this matrix gives me this other vector. So we want to solve for that. So how do we do this? Multiply the top by 3, 6, 3, 0, 3, 4, 0, 1. And then I'm going to subtract the bottom from the top, and that will be my new bottom row. So 3, 6, 3, 0. 3 minus 3 is 0. 4 minus 6 is minus 2. I'm actually subtracting the top from the bottom. 0 minus 3 is minus 3. 1 minus 0 is 1. Great. So I can divide the top by 3. That gives me 1, 2, 1, 0. 0 minus 2 minus 3, 1. And I want to get rid of this 2 here. So I'll just add the second row to the first. So 1, 2 plus minus 2 is 0. 1 plus minus 3 is minus 2. 1 plus 1, 1 plus 0 is 1. And then I have 0 minus 2 minus 3, 1. And there we have the inverse, which is this vector, this matrix here, right? So we verified that these are inverses here, and we actually derived this matrix N by, did I forget to divide? Yep, I forgot the minus sign here, divided by minus 2. And so now we've been able to derive the inverse, right? So to get the inverse, you set up the matrix and then the identity matrix, and you reduce it until you get the identity matrix on the left-hand side. So here's a 3 by 3 matrix. How do we find the inverse of that? 1, 2, 3, 2, 5, 3, 1, 0, 8 is our matrix. Okay, so what I'm going to do is multiply top row. I'm going to multiply it by 2, and I'm going to multiply the bottom row, row 3, by 2, and I'll just use a little annotation there to keep track of what I'm doing because it's a 3 by 3 matrix. So 2, 4, 6, 2, 0, 0, 2, 5, 3, 0, 1, 0, 2, 0, 16, 0, 0, 2. And so there is my new matrix. And then I'm going to get rid of the 2's in this column. And then I'll divide through again for row 1. So what I want is row 2 to become 2 minus row 3 to become, row 2 should be row 2 minus row 1, row 3 minus our row 1. And then finally, I want row 1, I'm going to just divide it by 2. So what do I get there? So row 2, take row 2, subtract row 1. 2 minus 2 is 0. 5 minus 4 is 1. 3 minus 6 is minus 3. 0 minus 2 is minus 2. There's my vertical bar. 1 minus 0 is 1. 0 minus 0 is 0. Row 3 is row 3 minus row 1. 2 minus 2 is 0. 0 minus 4 is minus 4, 16 minus 6 is 10, 0 minus 2 is minus 2, 0 minus 0, and 2 minus 0. And then I'm going to divide the top row by 2, 1, 2, 3, 1, 0, 0. And so now I have 1, 0, 0 in the first column. I want to get rid of this 2 and this 4 in the second column. So what I'll start off with is I will multiply row 2 by 2 and divide row 3 by 2. So 1, 2, 3, I'm not doing anything to row 1 here. And then I have 0, 2, minus 6, minus 4, 2, 0. And then 0, minus 2, 5, minus 1, 0, 1. And the point is now I can get rid of this 2 here and this 2 here by using row 2. So we'll make row 1, we'll replace it with row 1 minus row 2, and row 3 we'll replace with row 3 plus row 2, because they have opposite signs of the 2. And then we'll divide row 2 by 2. And what do we end up with? So row 1 is row 1 minus row 2, 1 minus 0 is 1, 2 minus 2 is 0, 3 minus minus 6 is 9, 1 minus minus 4 is 5, 0 minus 2 is minus 2, 0 minus 0 is 0. Add row 2 and row 3, 2 plus minus, 0 plus 0 is 2, 0 plus 0 is 0, 2 plus minus 2 is 0, minus 6 plus 5 is minus 1, minus 4 plus minus 1 is minus 5, 2 plus 0 is 2, 0 plus 1 is 1. And then we'll take the middle row and divide it by 2, so that gives me 0, 1, minus 3, minus 2, 1, 0. Let's go check my numbers. Yep. So notice that we've got 2 columns looking like the identity matrix here, and we just have 1 more column to go. So what I'm going to do is I want to get rid of this 9 and this minus 3. So I'm going to multiply the middle row by 3 and the bottom row by 9. So row 2 becomes 3 times row 2, and row 1 becomes 9 times, no, row 3 becomes 9 times row 3. And what does that give us? That will give us 1, 0, 9, and 5 minus 2, 0, because we're not changing that one. And then 0, 3, minus 9, minus 6, 3, 0. And then 0, 0, minus 9. And minus 45, 18, 9. Just going to double check my signs. Yep. Okay, good. So now I'm going to get rid of these 2 9s. We'll replace row 1 by row 1 plus row 3. We'll replace row 2 by row 2 minus row 3. And then we will replace row 3 by minus 1/9 row 3, just to get everything back to ones. So what do we end up with here? We end up with row 1, our new row 1 is 1 plus 0 is 1, 0 plus 0 is 0, 9 plus minus 9 is 0, 5 plus minus 45 is minus 40, minus 2 plus 18 is 16, 0 plus 9 is 9. Row 2, 0 plus 0 is, 0 minus 0 is 0, 3 minus 0 is 3, minus 9 minus minus 9 is 0, minus 6 minus 45, minus 6 minus minus 45 is 39, 3 minus 18 is minus 15, and then 0 minus 9 is minus 9. And then we'll divide row 3 back down by -1/9 to give me 1, 5, -2, -1. Yeah. And then finally, we can divide row 3 by 3. Row 2 by 3. And there is our inverse on the right-hand side. So that's how you can find an inverse. It's a little bit of a grind, but it's not too bad. Okay, you can check that this is the inverse to the original matrix by multiplying the two together and see what you get. So M inverse is the matrix. So -1 there means inverse. So there's M inverse. Not all square matrices have inverse, so when we look at determinants, we will see what the problem is. So solve the following systems of equations using matrix inverse. What is x1 and x2? We don't know, but we know we can set this up as the coefficient matrix, which is 1, 2, 3, 4. We have a vector of unknowns, x1, x2, and we have the right-hand side, which doesn't have a particular name, but it's B. Right, and so it looks like a nice linear equation, right? How do you find the solution to this? Well, we know that M inverse, we actually calculated that way up here. It's this matrix. So this matrix N here is the inverse to M. So so M inverse we found before is -2, 1, 3 halves, -1/2. So if we multiply both sides, these become the identity matrix. It's an arrow over the B. And the identity matrix times any other matrix is just equal to the matrix itself. So if I want my vector x1, x2, which is my solutions to my equations, all I have to do is take my inverse matrix and multiply it by the right-hand side. So -2, 3 halves, 1 -1/2 times 3 -1. -2 times 3 is -6. 1 times -1 is -1. 3 halves times 3 is 9 halves. -1/2 times 1/2 times -1 is +1/2. So there's my solution. And if I actually do the addition in there, I get -7. And then 9 halves plus 1/2 is 10 halves, which is 5. And if you plug that back in there, you'll see that that actually works as a solution. So if you have the inverse, you can just multiply to get the solutions. So here's the same thing. Solve the system equations using matrix inverse. M is 1, 2, 3, 2, 5, 8, 1, 0, 3, 8. That's our matrix. Note that there's a 0 x2 in here, right? So in the matrix, we need to put in a 0 in the right place, even though there isn't a term for it in the system of equations. And we actually know that M inverse is what we calculated above. That's minus 40, 16, 9, 13 minus 5, 3, minus 3, and 5 minus 2 minus 1 is the bottom row. Our vector of unknowns is x1, x2, x3. And the right-hand side, which is usually denoted by b, but doesn't have a specific name, is 4, minus 2, 1. So our equations can be rewritten as in matrix form as matrix of coefficients times unknown equals b. If we multiply both sides by M inverse equals M inverse times b, arrow on top of that. And again, M inverse times M is the identity matrix, I3 times X equals M inverse times B, but this is just X because when you multiply by the identity, just get whatever you got back. So M inverse times B. So the solution is minus 40, 16, 9, 13, minus 5, minus 3, 5, minus 2, minus 1, times 4, minus 2, 1. If we multiply that out, minus 40 times 4 is minus 160, plus 16 times minus 2, which is minus 32, and then plus 9 times 1. That's the first row, because it's the first row of this matrix times this column. 13 times 4 is 52, plus 10, because it's the minus 5 times minus 2, minus 3. 5 times 4 is 20, minus 2 times minus 2 is 4, minus 1 times 1 is minus 1. So this is 192 minus 9 is 183. 62 minus 3 is 59. 24 minus 1 is 23. And that should be the solutions to that system of equations. So if you square matrices can have inverses, they don't have to. If they do have inverses, then it's a useful thing for solving equations, and it says an important thing about matrices, which we'll explore next week.